So even before I will go into the presentation, I will remind you that here in Virtual Cell, we have a folder with tutorials. And in these tutorials, a lot of what you heard about is available. So say all the rule-based models here and rule-based EGFR, run. So there are three rule-based tutorials that you can look up. And the same is available at Virtual Cell support page, where you can see a lot of tutorials, and you can also go into YouTube channel and watch many more. So what is about rule-based modeling? Laszlo briefly mentioned that sometimes you deal with agents that have different binding sites, different states, and while the most people treat modeling as a modeling of reaction network, of a pathway, where each species corresponds to a variable, and then there are transitions between these species that are described by system of ordinary differential equations or partial differential equations if the species diffuse in space. In reality, each of these species is a multimolecular complex, where each molecule itself consists of multiple sites. And say for epidermal growth factor receptor signaling, while it is commonly initiated as ligand bound to receptor, then in fact you have multiple phosphotyrosines that you can monitor their phosphorylation time course, and multiple adapter proteins that can bind to phosphotyrosines one by one or in some combinations, and the mechanism by which they assemble into complexes may be known or unknown, but many people investigate these sub-processes. And investigation via regular reaction network modeling is impossible because chemical species in a reaction network is a pool of identical elements. And for identical elements, you have to distinguish between a receptor being phosphorylated on one side, on two sides, on receptor being bound to one adapter protein, another adapter protein. And here you can see that the amount of different combinations, each of them correspond to chemical species, explodes. If you want to track just 9 phosphorylation states, then it's 2 to the 9, 500 different chemical species alone. And then you bind adapter proteins to these phosphosites, and then you form dimers, and so on and so forth. And then there are multiple cases when you also end up with a multitude of different chemical species. The simplest is actin filament that can potentially go like pretty large, or binding of multivalent proteins that can form multiple topological configurations. And then like nephrin, NIC, and WASP system, and RNA granules. So there are multiple cases when you cannot do reaction network. But you also may be not ready to do spatial agent-based modeling because it's too complicated, and you just want to do it in like as a non-spatially. So for this case, you start with rule-based modeling, and you start with molecules that have multiple binding sites, and each of these multiple binding sites can have also multiple states. For example, receptor has a ligand receptor binding transmembrane domain to phosphotyrosines bound that can be unphosphorylated or phosphorylated. And these molecules, they form different chemical species. So, for example, EGF can bind to EGFR while binding through extracellular domain of a receptor. So, what's the trick? The trick is that we can define patterns when some of these sites can be unbound or can be in unknown state, undefined state. And this is a pattern that corresponds to EGFR with Y1092 sites being phosphorylated. And so this pattern may select a lot of different chemical species. So look here. It can be monomeric species unphosphorylated, monomeric species phosphorylated on another site, ligand receptor complex, another ligand receptor complex, dimers, and whatever you just don't know how many potential chemical species in the system are defined by this pattern. So once we understand the concept of a pattern, then the reaction rule is a binding or modification of reaction patterns. And here is a reaction rule corresponding to ligand binding to receptor. And as you see, there are multiple question marks on the receptor side, which means that ligand binds to receptor provided there is available extracellular domain, provided it is a monomer, transmembrane domain is not bound, and irresponsible of whether two tyrosines can be phosphorylated, unphosphorylated, or even bound to adapter proteins, indicated by these question marks underneath sites. So again, these are very small portion of all the different reactions that are generated by this reaction rule. So now with the concept of reaction rule, there is a next concept of the generation of a network. So if you have three rules, say ligand binding to receptor monomer, and then two rules of phosphorylation of a receptor once ligand is bound. So it's a very simplified system. So this indicates that ligand is bound, you see. These three rules are applied to the initial set of seed species. So we have EGF and we have EGFR, and they are just not, it has to be unphosphorylated. So given these two chemical species, the first rule generates ligand receptor complex, the next rules generate phosphorylation on one side, then reverse of the rule may generate complex without ligand, application of again either R2 to R3 to these two can generate the fully phosphorylated ligand receptor complex, and then reverse ligand receptor binding generates fully phosphorylated monomer. So you see that starting from two species, we end up with 1, 2, 3, 4, 5, 6, 7, 8 different species. And this is a network generation, which starts from species and reactions and generate the complete network. So this network can be very big, but at some point, if it ends up, like we exhaust the whole space of chemical species, then we say that we generated the reaction network model that corresponds to the original set of reaction rules. So this is what's called binary gen, sequential network generation, and then we can, after the network is generated, we can use the whole power of simulators to do time courses, to place the species into compartments, and maybe even provide diffusion for these individual species, and do partial differential equations, and so on. We can also do so-called network-free simulation that takes input seed species and rules, and immediately generates observables. So what does it mean? It's an agent-based simulation when we start with initial populations of initial species, and then the rules are applied to this initial population stochastically, and at each time point, we receive certain configuration of these of like bindings and modification states of these molecules. So if A can bind to B and B can bind to C, two individual rules, then we can generate AB, BC, ABC, and at each point, the number of all the different agents, the number of different combinations of these molecules is limited by the initial number of these molecules in the system, the number of A, B, and C. And then we can find out time courses for observables. And what are observables? Observables are, are exactly what we called pattern. So this is observable for a receptor being in phosphorylated state at 1092. What does it mean? It means that observable that is described by this pattern counts all the different chemical species in a system that has a receptor phosphorylated on this side. So whatever we have all the different molecular combinations, we just interested in how many phosphorylated receptors in these combinations. And this is observable, and the time courses of these observables are reported by NFC, network-free simulator. So one more important note that behind this graphical user interface, there is a processing engine, Binagen, that works with Binagen language. And there is a standalone Binagen simulator that is processing these strings. And sometimes you can work both ways. You can use graphical user interface, and then once you feel that you need something more advanced, you can export this BNGL file, edit it externally, and import it back into the virtual cell for further processing. So now I will do a very small demo, which is I open a new model, actually the existing model from tutorial, and this is rule-based EGFR compartmental, this one. So, and I will guide you through some of the features. So we have molecules, and this is, I said, EGFR with two tyrosines potentially being in 4 different states, each 2. So if you want to introduce new adapter protein, then we do new molecule, and this would be, for example, so we can rename it by right-clicking and saying rename. So as graphical user interface is very convenient, then you can anchor molecule. You can say that it's, for example, may exist only in cytosol and on the membrane. So we limit it to now this way it will never be in extracellular space. And if by accident reaction network generation will move it there, it will give you an error. And then you can introduce reactions. And reactions, for example, so we have a SHIC which has a phosphosite Y773, and we can create a new rule. This rule is in cytoplasm, and in cytoplasm, well, let's do it on a membrane. So why I'm doing it on a membrane? So new rule on a membrane. And on the membrane, we have a molecule Schick. And this Schick is must be phosphorylated, site Y773. And this site must be unbound. And another reactant is our new molecule SOS. And the result of this reaction is formation of a bond between Schick and SOS. And you see, it sometimes immediately start flashing red because it was phosphorylated and it wants to be phosphorylated also. And it's also like SOS now doesn't have a site to bind to Schick. So I have to go back to molecules and SOS, and I introduce site that I will call SOS. And now I'm going back to reaction, and I can say that before binding, this SOS site was unbound, and as a result, this I have a formation of a bond between phosphorylated Schick and SOS. And again, I don't want to take more time. There are multiple applications to do Bionogen style network generation. We create just a regular deterministic application. So if you click here new application, then you have a choice. Even though it looks something new, but rule-based models that generate network are just defined by deterministic application, because eventually you expand the network and this network is simulated just as a system of differential equations. And if you want to simulate it stochastically using network-free simulation, then you create a network-free simulation. So the rest is, if you're excited, you can check the lecture available on our YouTube channel. And also I will put extended slides to our Google Drive. Okay, any questions?